Welcome. I'd like to discuss with you the function f equals x to the 5/3 minus x. In particular, I'd like to discuss its concavity. Its concavity has everything to do with how the rate of change is itself changing and is given by the second derivative f prime. So as we go through this video, I'd like to talk about f, and I want to find intervals over which it is concave up and concave down, and I want to find its inflection points. Okay. So to that end, I've written f at the top here. So our main function is x to the 5/3 minus x. If we take the first derivative using the power rule, I get 5/3 x to the 2/3 minus 1. And so that tells us increasing, decreasing. And if I take the second derivative, the first derivative of the first derivative, I'm going to do the power rule again. I'm going to get 10/9 x to the minus 1/3, and that tells us concave up or concave down. So the SIGN sign of this one right here, so that tells us about the concavity. Right? It tells us concave up, concave down. If it's positive, it's concave up, and if it's negative, it's concave down. Okay, so what we want to do is we want to break the domain of this function, which is all real numbers. We want to break that domain up into intervals over which the function might have different concavities. And those are going to be witnessed by our function f double prime. I want you to note that this thing right here is also equal to 10/9 times 1 over x with a cube root about it, and that this expression right here is undefined at 0. It's undefined at 0, so 0 is a possible inflection point. If I try to set this thing equal to 0 and solve it, I'm going to find no roots. My f double prime has no roots. But that's okay. The concavity is just, the inflection points are just where concavity changes from up to down or down to up. It doesn't have to be where the second derivative equals 0. So essentially what we've realized now is that it's undefined at 0, and there are no other candidates for being inflection points. So we're going to partition the real numbers from negative infinity to infinity. That's the domain of the function, as those to the left of 0 and those to the right of 0. Okay, so we want to figure out, for the stuff from negative infinity to 0, what is the SIGN sign of f double prime? The only place the sign of f double prime can change is as it passes across 0. So if we know the sign of f double prime at even one x value over here, we know it at all of them. So I vote that we try, say, -1, and feed that into this expression and see what the f double prime value is. So if we feed f double prime at -1, we're going to get 10 over 9 times 1 over -1 is minus 10 over 9. So this is where I like to use my concavity arrows. And I'm going to put a concave down arrow there. So f double prime negative means the function itself is concave down. And I like to draw down arrows where that happens to be the case. So let's do the same thing over here at 1. Let's take f double prime at 1. It's going to be 10/9 times 1 over 1, which is just 10/9, which is bigger than 0. So from 0 to infinity, the function is going to be concave up. So note that even though f double prime isn't defined at 0, it's still an inflection point. It's still an inflection point. So inflection points are not just those places where the second derivative is 0, they can occur where it is undefined also. So our conclusion then is that f is concave up from 0 to infinity and concave down on negative infinity to 0. And all we need to know is the SIGN sign of f double prime to make that determination. Okay, so we know that it's concave up and concave down on these two intervals. I'd like to go ahead and go the distance with you and find the local minima and maxima, since we've already got a function here. So I've got the concavity, so we'll be able to use the second derivative test. So let's now find the critical points of the function and then classify them using the second derivative. So it'll take me just a second to erase this stuff. In the meantime, so our tactic is going to be to find the critical points and then find out whether the function is, well, figure out what it's doing in all of these different places. So, all right. So I want to find the critical points. It's going to be the thing I do next. So to find the critical points, I'm going to set the first derivative equal to 0. Note that the first derivative is everywhere defined, because I can always take this thing. I can always take x to the 2/3. So let's get the critical points by going 0 equals 5/3 x to the 2/3 minus 1. I'm going to add that 1 to the other side. So 1 is 5/3 x to the 2/3. How about we multiply by 3/5 to clear that? And now let's take, let's see here, the cube. Let's take this to the third power. I'll do this on the next line. 3/5 cubed is x squared. And then we'll take the square root of both sides, and I'm going to have positive, negative, square root of 3 cubed is 27, 5 cubed is 125, and that's equal to x. So these are my critical points. So I have two critical points, positive and negative root 27 over 125. We know the concavity there, which is awesome. So let's build ourselves a little table. So let's take our crit value, c minus root 27 over 125. And then we'll do the positive one, root 27 over 125. Let's see here. So here, at negative root 27 over 125, the function is concave down. Concave down looks like that. We've got a critical point where the derivative is 0, so that means that we've got ourselves a local max at root 27 over 125. And then for this one right here, it's going to be concave up, which looks something like that. So this one is a local minimum. Yeah. So, in summary, we took a function, we played through its first two derivatives. The second derivative gave us the concavity. The first derivative gives us the critical points, and then we classify those critical points by using the second derivative test with that information down there. We also found that 0 is an inflection point, x equals 0 is an inflection point, which is interesting because the second derivative isn't even defined at that place. So thank you very much for watching. I hope you have a lovely day.